So now to the moment I've been waiting for, which is the PID gain setup. See how the motor is being, we are setting the different gain. Now, just to recap what I've said earlier, but every parameter with this asterisk at its front are being stored on the module, the microcontroller on this PID module. So anything you update here is updated automatically. That's just what it moves. So this is the proportional parameter KP, the integral gain KI, and the differential gain KD. Now this last part is the cutoff frequency based on the filtering, the low pass filter that is being used to filter the velocity, the noise in the velocity reading. But now you don't need to touch this. It's this one generally works. You don't need to touch that. You understand? But we'll just focus on this KP, KI, and KD. Since now we have our maximum radius, but our maximum velocity we can send. Then this is the target velocity, and this is the different signals, the step, square, and sine signal for testing. Now this duration is just the duration at which the PID will run before stop. Whenever you want to plot it, this duration needs to run. If you want to change this duration, you can go back in and change the duration here. You change it to maybe 15 and come back. The duration is 15 and the graph has become what? 15. It's from 0 to time now from 0 to 15. So that's just to take note. I'll leave it at 10. I'll leave it at 10. Yeah, so the graph is now from 0 to 10. So now to set the PID gain, the first thing that we're going to set the proportional gain. Then next we're going to set the differential gain. Then we'll now set the integral gain. I'll be using the step input to set them. And what the proportional gain really do is just to increase the speed at which it reaches the set point or the target value. That's what it does. It's more like the driving force for the motor. How fast will it get towards to the target value? So that's really what the proportional is. And so the higher it is, the faster it or the quicker it gets to that target value or the set point. I'm going to set the target value. I'm going to limit it by 6. Now, normally try and make sure that this target value is greater than half of this. Yeah, just when that, we'll just make sure it's greater than half of this. So with that, I'm going to start increasing the KP. Let me start with something. Let me start with 100. I'll set it. I'll click on Start Pilot. I want you to notice the motor and the graph. Yeah. I know that with this now. But in this now, it's not yet as close to the target value where we want it. So we'll keep increasing. Let me go to 200. Let me by 2. Increase. Clear the plot. Start again. Yeah. So you see that now it's getting closer to the target value. Clear the plots and increase. Let me increase it by 2. 400 times 2. Set it. And start the plot. Yeah, so notice now there's a little overshoot beyond the target value. We're still not getting to the target value, but you see it's getting a little bit unstable here. My advice is to stop around here, but let me just for other tests, let me just try 600. Yeah, and this is like there's quite some unstable behavior already around this, and so I'll put it back to the previous value, or take it lower. Since 400 is start becoming a bit unstable, so I'll put it somewhere around 300 with length. Although there's an overshoot, there's a little wrinkles, but this is still okay. So with the KP being set, the next step is to set what's the KD. So I will just have to keep increasing we increase the KD. So what we want to do is to increase the KD. We increase the KD until this overshoot part is being dampened. That's what we want to do, increasing the KD until it is being dampened. This signal is becoming a bit smooth around this side. It dampens the overshoot. And understand something, that the more you increase the KD, the more you increase this KD, while it is adding this dampening, it is dampening this signal. So, but it tends to also reduce how quickly proportional rise. So you understand, it can, if you increase it too much, it will affect it. But no study with, but we need to remove this overshoot. This is not good to run the measure. So I'll start with 10. Cleanse. I start the plot. Yeah, you notice something. See, like as you know that those overshoots have dampened the. So I'm just going to maybe increase. Let me try increasing it to 20. Let me slide to apply. Very good. And yeah, this is actually the value what I'm looking for. We don't want that sharp. Not any power sharp. Wanted to treat a sort of curl while removing those overshoots. So now that is done, now I'm going to talk later about a special case of setting this KD, but that is for the next. That's what I'll talk about that next. But for now, let's set up the integral term, which is K. And you notice now that there's a kind of steady state error between the actual and the target value. But we want it to get to the target value. So this is where the integral term comes. So the integral term will remove the steady state error. But the point is you have to increase the integral term until the steady state error is reduced as much as possible without any form of overshooting. Yes, without any form of overshooting. That's what we want to do. So I'm going to cleanse. We'll create the integral term. I'll start with 100. Start plus. Yeah, noting that it's not as well. It's in steady state error. It takes time before it removes the steady error. So I'll just increase it again. Let's give it like 200 times 2. Play the plot. Yeah, I noticed that this is much better, but since it's taking much time before it removes that steady state error. So I'm going to increase it again times 2, which is 400. Set it. Start the plot. Yeah, notice now this is much better. This is very, very good. It has removed the steady state error. In other words, that's kind of completely removed the steady state error, and this is very okay. So let's do it again just to be sure. Yeah, this is good. Now you can increase it if you are not satisfied. But just to test the overshooting problem, let me increase it by 2 again, 800. Let me see the 2 overshoot. So that's how them. Yeah, and I wanted to notice something. Although it's more faster, but it's notice that it goes above. It's going above the target value before it settles down. So that's what we want to try and avoid. So it was 400 before. Let me put it at 600. Let me see what to output. And if not, see that this is now much more better. It's not overshooting. It's much more better. So we can stop there. This is very, very okay. So now we have fully set up the KP, KI, and KD. Now just can test this other signal. Let me try the sine. See that it's kind of follows the sine quite in a good manner. Yeah, so this is good. Sometimes can follow sine will compile. Now, this is where I'm going to talk about the special case, the square rule. Let me try the square rule. Yep. 12 long. Yeah. They say that it's responding well to the square wave. But the only problem with it in the square wave, noticing that the motor, when it stops, it's kind of jerking backward. You understand now? I'm noticing that whenever it's jerk, any behavior you see is exactly how it's behaving. That's what intuition doing really well. Noticing that when it's stopping, it's kind of jerking. It's kind of jerk backward. So that's a special case. I'm going to show you how to remove that. You understand now? So, but this is how to set your K pin, KI, KD, and test it. And before we go to this special step, just for I can add a lower value. Now, we can try it out with a lower value. And notice now, it's much better with the lower value. If I do this KI, 500, so I'll have to use 500. So let me just try something Monday, a negative value. Just as a final test, let it load. We can try out the options, whatever you like. So you see that this is global. Whether I'm running a positive command or negative, angular velocity command will work properly. So that does it.